All right. Well, hello and thanks for tuning in. Um, we'll take a look at today's content here. Okay. All right. So we will continue where we left off on Friday. I kind of showed you a few different linear models where we fit polynomials of different orders, and I said, the traditional way we would evaluate, say, fitting some models to some data would be to use something like the AIC or the BIC, or we would look at the summary table for the coefficients and see which of these coefficients are valid, okay, or are significant. So I think we had this Olympic data set where we are trying to predict the gold medal winning time for the 100-meter dash, and we're using the X variable, which is the year in which the Olympics were held, as our predictor variable. And so we tried fitting a second order, third order, a linear model, as well as quadratic, cubic, fourth order, fifth order, sixth order polynomial, and we plotted them, and this is what they looked like. And we want to be able to kind of evaluate which of these things, which of these models would be the one that is going to work out to be the best. So that's kind of the classic approach, okay? Classic approach kind of requires us to do some thinking about the variables, and sometimes it puts us in these slightly uncomfortable positions of trying to justify why we chose a certain model. So, for example, does it make sense for us to say the race time of the winning race time has a cubic relationship or quadratic relationship to the time or the year in which the race was held? What about a sixth order relationship? And how do you justify something like that other than to say, well, when we fit the line to the data, it looked good, okay? We don't really have logical reasoning to kind of back this up. The tools like the AIC and the BIC, which are measures that we can use, also kind of help, but at the end of the day, it does require some thinking and things like that. What I'm going to introduce today is cross-validation. Cross-validation removes the requirement for us to do this kind of thinking. And this could be seen as either a good thing or a bad thing. It's a bad thing if you feel like, the thinking requires, this skillful thought and careful thought process. And if you remove that, maybe we're not doing a great job with the data. Or on the other hand, you might say it's actually an improvement, because at the end of the day, some of the decisions we're making are just kind of arbitrary. We just say, hey, you know what? It looks kind of good in my opinion, so we're going to go with that. And so rather than just having kind of this arbitrary decision-making process, we just have kind of this clearly defined thing that doesn't require any thinking, and it just says, hey, this is how we're going to define better a good fit, and we're going to just kind of move in that direction. And so cross-validation uses what we call a validation strategy. Okay, the way it works comes down to this: we have the available data, and ultimately the goal is to fit a model to our available data so that it is going to make good predictions for future data, okay, data that we haven't seen yet. Now, we don't have the future data yet. We can't travel to the future and know exactly what's going to happen. So we simulate this. We pretend to have a this kind of setup where we're going to split our total observed data into a training set and a validation set. We'll use the training set to fit the model, okay? And so, for example, if we're doing linear regression, fitting the model is just figuring out what your slope and your intercept parameters are. And then after we fit that model and we figure out what slope and intercept we have, we validate it against the validation set. We just we plug those parameters in, we make predictions, and then we can measure how good our predictions are against the validation set. And so this kind of simulates, it's kind of like rolling back the time and saying, okay, you know, today is what, we're in 2024, so we're going to just pretend we have data up through the year, you know, 2020, and then we're going to pretend like using our model, and we train it on data up through 2020, how well can we predict data for the years, you know, 2021 through 2024 or something like that. So we're kind of putting ourselves, you know, simulating this idea of having a model on our current data and seeing how well it performs on kind of future data. And so we just kind of force this upon ourselves. We split our data into a training set and a validation set. We make predictions for the validation set, and then we have a way to measure our performance. And so we have some kind of metric. Frequently we used mean squared error, but there's other metrics as well that we can use to kind of measure how well our model performs at making our predictions. And we use that metric as a guide to say, hey, this model that we fit, when we fit a linear model, its mean squared error is this on the validation set. When we fit a quadratic model, its mean squared error is less or more. And we use the performance of this metric to decide which of our models is the best model here. All right, so kind of one of the methods of cross-validation that we'll look at will be leave one out cross-validation. So in leave one out cross-validation, the validation set is just one observation, okay? Which, you know, it feels a little bit silly. It says, you know, we have a training set and a validation set, but basically the training set is going to be all of the observations except for one, and then the validation set is that one observation that you left out. And when you do this, every data point in your data set gets a turn at being the validation set. So you end up having kind of n of these training validation splits. So I'm going to demonstrate how leave one out cross-validation works with this toy data set here. Okay, so here is our toy data set. It's going to x is 1, 2, 3, 4. T, the values that we're trying to predict are going to be 1, 3, 2, 4, and this is how I'm going to set up my training and validation set. I'm basically going to take the fourth observation. I'm going to write index 4. That's going to be my validation set, and so and then I initialize a total squared error at 0, and we're going to kind of add to it, accumulate to that to calculate our you know, mean squared error metric here, okay, or total squared error here. So we take our x values 1, 2, 3, 4. I'm going to subtract off observation 4, so I'm going to do x minus the index there, and then that value that I've left off, the x subset index, is going to be my validation x. Okay, I do the same thing with t. I take t, I subtract off the index, and I subset just to the index. That's going to be my training t and my validation t. My training data is going to be a data frame where x is the training x and t is the training t. So basically my data frame is going to be 3 rows, 1, 2, 3 for x and 1, 3, 2 for t. And we are going to fit a model on just those data points, 1, 2, 3 and 1, 3, 2. And I'm going to say, hey, fit a linear model, predict t based on x using our training data. And so our full data set looks like this: 1, 1, 2, 3, 3, 2, 4, 4. Our prediction line for the full data set is going to be 0.5 for the intercept and 0.8 for the slope. when we do our first training split, we're going to take this observation 4, 4. This is we're going to remove this data point. Okay, so I'm going to like cover it up. And so with just the 3 remaining data points, which I have 1, 1, 3, 2, and 2, 3, what is the line that best fits this data? All right, so when you fit the linear model just to these 3 points, the line that best fits this data has an intercept of 1 and a slope of 0.5. This is the best fitting line when you fit fit a linear model to the remaining 3 points. And now we take the data point that we left out, which was 4, 4. Okay, we're going to put that in, and we're going to measure how much error do we have. How well does the straight line that we created, this we're fitting a linear model, how well does this linear model predict the data point that I left out, the validation point? So the actual value is 4. The line, if you plug in x equal to 4, the line predicts 3. Okay, so we have a residual of 1 between the actual value and the predicted value. And when you take that difference, you get 1, and you square it. Your squared error there is going to be 1. Okay, and so to kind of keep track of this, I'm going to take my squared error. I'm going to add 1 to the total squared error. Remember, I initialized total squared error at 0, and so I'm going to add 1 to it. Okay, and so this is just kind of the code to do it. I said, you know, create a model, leave one out model using the training data. We're going to make a prediction using the leave one out model using the new with new data, where x is the validation x. Basically, right now we're just plugging in the value 4, and so t hat, you know, according to this picture, t hat is 3. And we're going to calculate our squared error by taking the validation t, which is the value 4. We subtract off 3, which is t hat. We square that, which is going to be 1 squared. Our squared error is going to be 1. Initially, our total squared error is 0. We do 0 plus 1. Our total squared error so far is 1. Okay, let's do this again. Now we're going to go to the next data point. We're going to remove, I'm going to go to, I think we removed the 3rd data point here. So here's the line if you fit it to all 4. But if you remove this data point, and now you just have a point at 1, 1, 2, 3, and 4, 4, what is the line that best fits the data? Okay, so if you only have those 3 data points, the line that best fits your data looks like this. Okay, this is the line that best fits the data. It has an intercept of 0.5 and a slope of 0.92857. Okay, this is the line that best fits that. Now we're going to plug in the data point that we left out, which was at 3, 2, right here. Okay, we're going to plug that back in, 3, 2, and we're going to measure how much error is there between the actual value of 3, 2 at 3, the actual value is 2. What value did we predict? According to this line, if I plug in 0.5 for the intercept and my slope is 0.92857 and I plug 3 in there, the number I would predict is 3.285. Okay, 3.285. So this value right here. How much of a difference is there? That difference is going to be 1.285. Okay, 1.2857. So that's my difference, and I'm going to square that difference. So my squared error for this data point is going to be 1.653. Okay, we keep going. Now I'm going to subtract the 1 data point that I leave out is going to be my 2nd data point. So I'm going to kind of cover this up, and we're going to say, hey, what is the line that's going to best fit the remaining 3 points? So the line that best fits the remaining 3 points looks like this. This has an intercept of negative 0.14 and a slope of 0.92857. Okay, this is the line of best fit here. And we're going to say, okay, well, how far off is it from the actual point? So if I plug in the point that I subtracted out, 2, 3, That's right there. How different is it from what the line predicts? Okay, the line, if you plug in x equal to 2, okay, the line is going to predict this value 1.714. How different is the actual value from there? And so, this, well, this you have an error of 1.2857, and then you're going to square that difference. 1.2857 squared gives me 1.653. Okay, I hope so far this is good. And then we do it one more time. Okay, so again, here's our full data set. Now I'm going to leave out the point at 1, 1, and I'm going to say, all right, for the 3 remaining data points, what is my line of best fit? Okay, for the 3 remaining data points, this is the line that best fits these 3 points. Intercept of 1.5, slope of 0.5, and when you plug in 1, the line predicts a value of 2. Okay, so we bring back in the data point that we threw out, the one we left out, and we say, okay, how far is this difference? This difference gives me a difference of 1, actual value 1, predicted value 2, difference of 1. We square that difference, we get squared error of 1. So if you've been keeping track, our first value had a squared error of 1, then we had 1.65, and then 1.65 and 1. And so when you add them all up, the total squared error is 5.306. The total squared error across the 4 data points, each one being one of the points that we leave out, our total squared error is 5.306. And therefore, our mean squared error, I take that and I divide by 4 because our data set had 4 values. Our mean squared error is 1.3265. Okay, that's our mean squared error. And so this is the metric that we use to evaluate this is one way for us to use cross-validation to evaluate this. Okay, so for a linear model fit to our 4 data points, our mean squared error is 1.326. Then we could try, say, a quadratic model, all right, and do the same kind of process. And we can say, all right, how much error is there between a quadratic model and the predicted point? And we would do that, and we would be able to then compare the mean squared error for the linear model versus the mean squared error for a quadratic model, and compare the performance between these 2 things. Okay, let me give you your first view quiz answer, which is the letter D. D as in dog. D as in dog is your first view quiz answer. Okay. R has its own cross-validation function, and it works by fitting a GLM model, and then you can do cv.glm, and there's different aspects to it, and it's all part of the library boot. So if I load up library boot, I can take our data frame. You create a data frame with all 4 data points, or your full data set. So x is 1, 2, 3, 4, t is 1, 3, 2, 4, and then I say fit a linear model between t and x, and then I say, hey, leave one out cross-validation. So that's done with doing cv.glm, cross-validation.glm. You give it all the data. And we're going to try to do it on the linear model, and then it does leave one out cross-validation. You ask for delta 1, and this gives you basically your mean squared error here. And so it says, yeah, your leave one out cross-validation mean squared error is 1.326531, which matches exactly what we got. Okay, and our process of getting 1.326531 was done by taking all of these squared errors. We did 1 for this one, and we got 1.6531. For this one, we have 1.6531, and for this one, we have 1. So when we add up those 4 values all together, you get 5.306 divided by 4 is 1.326531, and indeed, we get the matching value when we do leave one out cross-validation and using R's boot package here. So just for clarification here, when you do cross-validation to evaluate a model, you get one cross-validation score for that model. It's usually the mean of the different kind of cross-validation errors. So in our toy data set with 4 points, we performed leave one out cross-validation, and we had to see like fitting 4 different models, and we had kind of squared errors, 4 of these different squared errors, and we added them up and we divided them by 4, and that one number, 1.3265, okay, is our cross-validation score for a linear model. And we would then try this again with, say, a quadratic model or something, and you would fit a quadratic model 4 times. You'd get a different cross-validation score each time, and you would add them up. I'm sorry, cross-validation number, and you would add them up and divide by 4 again, and you'd get a some summary value for the quadratic model. Okay, so I guess this is just summary slides. So again, we did 1 squared error 1.6531, 1.6531, and then 1, and then you added them all up and you divided by 4. And so the mean is 1.3265. We could try other things like a polynomial model or a log-log model, and by kind of comparing the cross-validation scores from these different models, we get a sense of how well each different model performs. Another cross-validation method is k-fold cross-validation. This is probably the more popular and preferred method, and that's because leave one out cross-validation can become very, very, very computationally expensive. So, in our toy data set, we only had 4 data points, but most data sets probably have hundreds, some perhaps more. Maybe not as many, but you might have a whole bunch of data points. And with leave one out cross-validation, you have to fit a model for every single permutation where one data point is left out. So if you have n data points, each one of those data points gets left out at some point in time. You have to fit n of those different models, make a prediction for that one data point that got left out. So it's very computationally expensive. Okay. Another issue that you could run into is that all of these models could end up looking really, really, really similar to each other just because all of them, their data sets look almost identical to each other. So the resulting kind of coefficient estimates often end up kind of highly correlated, and you could still run into the problem of overfitting your data. So if you have a large data set, an alternative is to do k-fold cross-validation. Okay, with k-fold cross-validation, we take our data set and we partition it into k approximately equal-sized blocks. So k might be, say, 4, and you're going to take your full data set and you're going to divide it into 4 chunks, and then each chunk or each block will serve as the validation set, whereas the remaining blocks, so if you have k equal to 4, 1/4 of your data will be the validation set, and the remaining 3/4 or 75% will be your training data. You fit the model to the training data, and then you have the model make predictions on the validation data, and you measure its performance there. So this is kind of an illustration. You split up your data into these 4 chunks, and for the first iteration, you train on these 3 sets, and you validate on this set. Then the next iteration you validate on the second set, validate on the third set, validate on the 4th set. So each block has a turn being the validation set. So let's try this out for our Olympic data set. Okay, so our Olympic data set, we have a total of 28 observations, and I'm going to do 4-fold cross-validation. And so we will divide our 28 observations into 4 random sets. So I'm going to kind of shuffle up our data, and we're going to have basically 4 sets of 7. So here is the full data set with all 28 points. And what I'm going to do now is I'm going to divide the data into 4 random blocks. And for each of those blocks, we're going to try fitting a few different polynomial models. Okay, first we'll fit a linear model, then we'll fit a quadratic model, a cubic model, 4th order, 5th order, 8th order, and then just for fun, we'll fit a 17th order polynomial. Okay, and for each of these things, we'll calculate the total squared error for each model, and then we'll calculate the cross-validation score by averaging the squared error for each model, and then finally at the end we'll compare the cross-validation scores to kind of select our model. Okay, so the way I'm going to do this is I'm going to just shuffle the values 1 through 28 because I've got 28 sets, and then once I've shuffled 28 observations, and I'm going to create 4 sets. And so after I shuffled those indices, I'm going to just put the first 7 into set A, the next 7 into set B, the next 7 into set C, and the last 7 into set D. Okay, so this is I've got all of the different sets here. I'm going to store all of my total squared errors in each of these different vectors. So this is going to be my cross-validation. So remember, we get a total squared error for when set A is the validation set, and then I get total squared error when set B is the validation set. And so each of these things we're going to have 4 values to fill in. And this is kind of the code that we could run if I'm going to do cross-validation manually. So first I say, all right, I'm going to do this 4 times because I have 4 validation sets. Okay, and so I go to kind of the sets which have the different indices here, set A, set B, set C, set D. And so the first iteration, I is 1, validation index will just kind of be my 7 random observations that belong to set A. My training data will basically be everything but those validation sets. I'm going to take my Olympic $year and subtract out the validation indices. I'll do Olympic $time, and I'll subtract out the validation indices. And then for my validation set, my validation X and validation T, I'm going to subset just to those validation indexes or indices. My training data is a data frame consisting of my training X and training T. My validation data is a data frame consisting of validation X and validation T. Okay, and then here I'm just going to say how many observations here. N is going to be 7 because I've got 4 values in my validation index. I'm going to fit my first model, which is just a linear model, which I'm going to say predict T based on X using just the training data. After I make that model, I'm going to then ask it to create predictions on the validation set using that model. And so these are going to be my predictions. Then I want to know how different are the actual values from the predicted values, T hat. So I'm going to take the actual values from my validation set, $T minus the predicted values, T underscore hat 1. These are the values that I just predicted. I'm going to square those differences. I'm going to add them up, and then we'll divide by n. So we get kind of a mean squared error here for our 7 data points there. I'm going to do the same thing. This time I'm going to try it using for the same validation set. We're also going to try fitting a quadratic model. So I'm going to say predict T based on poly x2. This is going to kind of take x and make a quadratic transformation. It'll still have the linear component, but basically we'll have multiple columns, a column for x and a column for x squared. Using just our training data, we're going to ask make predictions using that quadratic model and calculate the differences. Okay, and I continue this, and so the full kind of thing looks a bit bigger, but all of these lines are pretty much the same. They're almost all exactly the same. It's just rather than a 2nd order polynomial, I have a 3rd order polynomial, 4th order polynomial, 5th order polynomial, 8th order polynomial, and then also a 17th order polynomial. Basically, all of these things, I'm just saying create a linear model where we're going to predict t based on the polynomial transformation of x. That creates the model 3 or model 4 or model 5. Using that model, make predictions using the validation set. I say predict using model 3 on the validation set. That's going to be t hat 3. Then we take the difference between the actual values and those predicted values. And we say, hey, what's the squared difference? Add them up, divide by n. Same thing. Fourth order polynomial, fit a fourth order polynomial model, make predictions using that fourth order polynomial model, take the difference between the actual value and the predicted values, square those differences, add them up, divide by n. And we do this for all of the different models that we're trying to fit. And so let me just illustrate what this kind of looks like. Let me give you your second view quiz answer, which is the letter E. E as an elephant. E as an elephant. Okay, so here is the full data set, 28 observations. These 7 red points are my validation set. Okay, this I guess is set C. So we selected 7 points at random. These are the 7 points at random. And so what we're going to do is we're going to make these 7 points disappear, and we're going to fit a linear model on the remaining 21 points. So if you remove those 7 points, the remaining 21 points look like this, and the linear model that fits the remaining 21 points look like this. Then we bring back those 7 red points, and we say, how well did this line predict those 7 points that we left out? Okay, so these are the 7 points we left out, and we see, oh, okay, this is, some of these are predicted really well, like these dots are like almost exactly on the line, and then, we got some residuals over here, right? And so if you say, hey, what's the mean squared error for these 7 particular values, our mean squared error is 0.0319. Here's again the full set with the 7 points in red, just highlighted here. Now what we're going to do is we're going to take away these 7 points. We're going to leave them out. With the remaining 21 points, we'll fit a quadratic model. Okay, so this is a quadratic model that's fit after you remove the 7 points. Then we bring back those 7 points and we say, how well did the quadratic model predict there? And so we see, okay, you know what? We have a little bit of error everywhere, but we don't have any huge residuals, and so overall the mean squared error on this set is 0.025. So on these 7 sets. Okay, again, looking at the full data set, here it is with all 28. Our 7 data points in our validation set are still highlighted. I'm going to, again, subtract those out. On the remaining 21 points, we're going to fit a cubic model. This is what it looks like. Okay, this is the cubic model fit to those remaining 21 points. And then we say, okay, let's bring back those 7 points. How well did it predict? And we do this. And we get our mean squared error here is 0.0131. Okay, we have small, really small residuals for a lot of these things, and pretty small residuals for, say like these 3 points, and this one's still pretty small. So mean squared error is that, and we just kind of keep going. We just say, all right, let's try it out for, say, the 4th order polynomial or the 5th order polynomial or something like that. Okay, so again, here's the full data set with all 28 points. We're going to hide 7 of these points, okay, these red points, and we fit the 4th order polynomial. So this is the 4th order polynomial that gets fit to our data. We bring back those 7 points that we left out, and we ask, okay, how well did it predict? And it's we get 0.0192. Okay, sure, no problem. 5th order polynomial, if we remove those 7 red points, this is the best fitting line for those 7 red points, and we can see, this is an 8th order polynomial. 8th order polynomial, we can see, there's a lot kind of more flexibility in the thing, and we say, okay, well, how well did it predict the 7 points that we left out? Okay, and we can see our mean squared error is starting to climb actually back up. And we have issues where, because we left off this point with the 8th order polynomial, things are starting to kind of curve around and things like that, and so we end up getting kind of a big residual right here. And so this our mean squared error starts to tick back up a little bit. Okay, and I think this one's the 17th order polynomial. So again, here's the full data set. I'm going to hide the 7 red points, and on the remaining 21 points we're going to fit the 17th order polynomial. So the 17th order polynomial has really high flexibility in our data, and so it's able to fit all of these things, and these points it's actually able to fit like perfectly, and it gets for the actual data. And I think if we saw this, we would say, oh, this is certainly overfitting the value, right? And this is where cross-validation comes in and confirms that we have overfit the data, because here we're probably getting really good fit for these 21 data points. The 21 data points that we used to train, we're getting really small residuals in our training data. But then I bring back those 7 data points that I left out. Okay, I bring back the 7 data points, and we see we're not doing a great job, because with our training data, some data points right here were left out, and so it just kind of wiggled around, and so now we have huge residuals here. And then this data point right here, it actually, the prediction line just kind of rockets off to the very top, and so we have this huge residual. Okay, and the mean squared error ends up being this ridiculous number, 1,640. Just this huge residual, just because this prediction line that was fit to the 21 data points just does not do a good job of predicting the values that we left out, the 7 values that we left out. So it does a good job of fitting some of these points, and avoids having with a 17th order polynomial, it's able to fit the training data really well, but then we see, yeah, it's not doing a good job on predicting the values that we left out. So this is kind of how cross-validation works. Okay, so here I have gone and I ran the calculations for the different validation sets. So we had validation set A, validation set B, validation set C, validation set D, and then we would take the average. So for validation set C, I think these are the different numbers that we ran across. So most recently we had 1640.9249, and the 8th order polynomial over here we had 0.0213, and that's this value 0.0213, and so we have all of these things. And so, we just looked at the pictures for validation set C, but you would have similar pictures for validation set A and B and D and things like that. And each of those, you would have 7 different points, for set A. For validation set B, you'd be a different 7 set of red points, and validation set C, you'd have another 7 random points. And so the overall cross-validation score for the linear model is going to be the average of all of these things. And so the overall cross-validation score is 0.0674. For the quadratic one, the overall thing is 0.0624. We're just taking the average of each of these things. 0.046, 0.029, 0.0131, 0.1403. We take the average, we get 0.057. And we would look at this, and so we can see the 17th order polynomial gives me a cross-validation score of 525, so that's very bad. And we kind of go with like the lowest cross-validation score. So we're looking at this, and we end up seeing that the 8th order polynomial gives us the lowest average cross-validation score. For validation set A, it was 0.0334. For validation set B, it was 0.0320. For set C, it was 0.0213, and for set D, it was 0.0809. And so my average ends up being 0.0419. And so based on this, we would say, oh, okay, you know what, the 8th order polynomial has the lowest average cross-validation kind of squared error. And the 3rd order one has the 2nd lowest at 0.0571. And so we would pause and we would think and say, hey, which of these models should we use? Now, I would say use the 3rd order polynomial, but you know, if we're going straight off of the cross-validation score, this one is the lowest, 0.04. Okay. One thing you have to keep in mind, though, is that the validation sets that you have, they are random. So these cross-validation scores are subject to randomness. And so one thing that's recommended is that if you're going to do something like k-fold cross-validation, you should run it a few times. So this is one of the disadvantages of k-fold cross-validation, is that these cross-validation scores are subject to randomness, and that it's the randomness of how the validation splits got split up. So here, you know, basically we're taking all of the observations and we're just kind of mixing them up and putting them into different chunks. And depending on which observations end up in, you know, chunk 1, chunk 2, chunk 3, or chunk 4, or, you know, whichever chunk you're talking about, because of randomness, your cross-validation scores could end up being different. So here I ran the same code again, this time with a different seed, okay? And so we end up with different validation sets. And using different validation sets, we see the 3rd order polynomial performs the best at 0.0464, and the 8th order polynomial is 2nd worst, okay? Quadratic is 2nd best, and I can try this again using another random seed, and with another random seed we get 3rd order polynomial, again performing the best, 0.0581. Here the 8th order is the 2nd best at 0.0603, and then quadratic at 0.0661. Okay, so there is randomness, which is a factor when you do k-fold cross-validation. So if you have the computational expense or budget to do more randomizations, then it's often recommended to do a few of these things. Okay. Meanwhile, when you do leave one out cross-validation, because every single observation is part of the validation set, there is no randomness. You can do cross-validation with library boot, and you can do cv.glm, which is in library boot, and here you can set your k. Okay, k is going to be the number of folds. If you leave it blank, k defaults to being n, or leave one out cross-validation. And so the score that it provides is going to be your average squared error. So, so I run cv.glm a few times for each of these models. You're going to see some variation because the random blocks are different with each run. Meanwhile, when you do leave one out cross-validation, there is no variation. Okay, so here, for example, for a polynomial linear model, I just do poly 1, or I could have just done year. cv.glm, you know, produces slightly different cross-validation scores, 0.064, 0.0659, 0.0576. Okay, so every time I run it, I get slightly different cross-validation scores. If I do a quadratic, I get 0.062, 0.0469, 0.0648. If I do cubic, I get 0.049, 0.064, 0.0709. And, you know, you have to kind of decide, all right, which of these models do I want to run? And, you know, all of these, they all end up kind of the amount of, I guess you could take the average of these three, the average of these three, and compare it to the average of these three, and make a determination that way. But yeah, k-fold cross-validation is subject to some random noise there. Okay, Whereas when you do leave one out cross-validation, which is done by not setting k equal to anything, so k equal to 4, we'll do fourfold cross-validation. Here I've got 28 observations, so if I just say k equal to 28, or if I just leave it blank, it's going to do leave one out cross-validation. And because of that, every single time I run it, I get the exact same value. There's no variation from run to run, and so everything produces the exact same value. But again, this is a lot more computationally expensive because we have to fit 28 models and calculate the error for every single data point. Okay, so that's kind of how cross-validation works. Let me give you your last view quiz answer, which is the letter C. C as in cat is your third view quiz answer. And this is just kind of a summary regarding cross-validation taken from Wikipedia. So cross-validation is a method that we use to see how a particular model will generalize to new unseen data, right? The goal of cross-validation is to kind of test our model's ability to predict new data which that wasn't used as part of the training process. And this helps us avoid problems like overfitting. Overfitting is the thing where you get it really good performance on the training data because you've added all of these things and it's able to make really good predictions on the training data, but it performs poorly on new data because you overfit your training data. And so cross-validation helps us avoid those situations. Multiple rounds of cross-validation are performed using different partitions, and the validation results are combined or averaged over the rounds to give an estimate of the model's predictive performance. And if you're capable, if you have the computational capacity to do it, you would then do even multiple rounds of k-fold cross-validation itself to get like an even better sense of how well a model performs. Okay, we'll wrap it up here. Thanks for watching the video, and be sure you respond to the view quiz, and we will see you on Wednesday.